Okay, good afternoon, everybody. I hope everyone's having a wonderful day. I want to welcome you to CS 340, Advanced Data Structures and Algorithm Design. My name is Dr. Daniel Page, but you can just call me Dan or Daniel. I'm looking forward to meeting everybody. I'm seeing some lovely faces on the video. And by the way, if you ever find yourself having any questions, feel free to put them in the chat or stop me to ask me them. I'm very happy to answer any questions, okay? So if you're wondering where you can reach me at daniel.page@uregina.ca or through your courses on our course website. And what we're going to do today is we're going to go through the course outline a little bit. I'm going to highlight some things. I encourage you to review these things. And then we'll get started on talking about some standard framework stuff that I need to lay out for everybody so that we could kind of talk about problems and data structures and all that kind of framework stuff so we could kind of build up and start talking about problems, which is going to be a really big part of this course. So I'm going to move over to my table over here and we're going to talk a little bit about the course outline. Is that okay with everybody? Give me 2 thumbs up. Okay, great. Wonderful. So let me just head on over here. Okay, let me just, there we go. So if you have any questions while we're doing this, just interrupt me verbally because I can't see the chat just at the moment here. So please just interrupt me verbally. It makes things much easier. So first, if you haven't had a chance to take a look at the course outline, like I said, do give it a quick review. I put a lot of details in here to be very helpful. So if you're wondering where my office is, I'm working remotely. So there's no magic office to go to see me on campus. Just come and drop me an email. I'm usually quite diligent over email. So if you send me a message, I'm pretty likely to respond to you pretty quickly. Or if you send me a message over your courses. I have office hours, so I have three blocks for office hours. I try to make sure I'm available for students so I carefully look at what other classes are going on. So I try to schedule them so there's some time that you might be available. So these are the times I'm going to be available for office hours. So for example, I was just in office hours not too long ago. But you'll find that I put a pretty nice spread over the hours available. So to be in this course, you had to have gone through CS 210. So I'm hoping that everybody's gone through that just fine. Now, a couple of things. Just the first thing I want to point out is that there is no required textbook for this course. However, you'll find very often that having a supplemental textbook can be very helpful. So for example, I highlight a few books here. One that's very common that this university has in their bookstore is this one by Weiss, Data Structures and Algorithm Analysis in C++. This book is very commonly used in this course, but I'm not going to require you to have it. A lot of the things I talk about in this course are in that book, but most certainly not everything. There's not one size fit all with this course. A lot of the material follows. It's generally a combination of several resources, but here's the cool part. All the resources for this course are self-contained. So I will be providing, as I'm going to mention, lecture notes. So we'll be doing lectures together where I'm going to do the notes together with you on the board here. So I encourage you to take notes. But for the sake of accessibility, and if ever I need you to kind of point at you and say, hey, look, can you read this one thing? I'll put it in the notes. And also, if there's ever a time where we need to do more examples, or if you ask me for some more examples, I'm happy to make more available for you, okay? So there's a few books here. So the Weiss book, another book is this one by Corman, Lyserson, Revest, and Stein. It's usually abbreviated as CLORS. This is a pretty standard algorithms book. It's a very good reference text. A lot of the more formal aspects of this course are it's a pretty good reference text for a lot of those things. A lot of people I know over the years, like when they're like, hey, look, I need a really good book that collects up a whole bunch of data structures and a bunch on algorithms. This is one of the good books to get if you find yourself looking for a supplemental text. That's just a matter of reference. Actually, I do outline the parts of the course that for each one of these books, it's rather helpful. So if you can get your hands on any of these, they're pretty handy. One that's a little bit harder to get your hands on but it's also a good book. It's very relevant for the latter parts of this course and some of the more formal aspects of complexity theory. Is this one called Algorithm Design by Kleinberg and Tardos. I like it because it gives you a lot of, it's very much from the framework more of, hey, look, where did this idea come from? And you think of it more as the algorithm designer or somebody that comes along and wants to discover what the algorithm is like. Where did the idea come from? You'll find very much that this book is just baked in that kind of mentality. And I know some people find that very helpful. But yeah, no, so in this course, we'll be looking at data structures and algorithms to solve problems. And one important aspect of it that's going to make it feel a little different than 210 is the fact that we're going to focus a lot more on analysis. So we're going to see a lot more data structures, more algorithms, but you're going to see I'm going to take more of this formal approach where we're going to look more at where the ideas come from and why the things that I present you, like why do they work? So we're going to spend a lot more time on that than we would have in a class like 210. So just a general flavor for what we'll be doing here. Here's just a general breakdown of the course topics. So we're going to start off first with, like I said, just this general framework. So some of this will be review for you. For some of you, it might be new. That's okay too. That's okay too. We're going to see a lot of stuff at the beginning of this course where I'm just going to kind of make sure everybody's on the same footing. I like to call it, like, I'm trying to lay that framework down so we're all generally talking about the same things. Then I'll talk more about algorithm analysis. So some of this will be review from 210, but done a little bit more formally. And then I'll talk about asymptotic notation, then move into talking about properties that asymptotic notations have. And we'll do some examples of analyzing the running times of algorithms. We'll also look at proofs of correctness as well. Like, how do we know an algorithm actually works? Some of this stuff we may have touched upon in 210, but most certainly some of this will be things that will be built upon a little further. One other thing that is an interesting topic we'll talk about near the beginning is also the idea of lower bounds and trade-offs. So very often we'll talk about, if I want to give you some problem and I want to know what's the fastest algorithm I can throw at you to solve that problem. I would like some way I can actually demonstrate to you that that is in fact going to be the case. And what can that reveal to us to figure out and learn how we can solve other problems? So we'll see a few different techniques for proving lower bounds in this course, in this part here. So that's the main first part of this course. The second part, we're going to talk more about data structure. So I'll be picking up basically from where 210 left off. And I'll start introducing you more analytical techniques, such as amortized analysis, which is a special kind of worst case analysis. I'll show you some interesting relevance it has to practice versus theory, and also how we can use it to kind of in some general settings. Then I'll do a bit of a review on trees, and we'll talk about some priority queues. So a priority queue ADT is a generalization of a queue. And we'll talk about heaps. You may have seen some bits about this in 210. For example, you may have seen for example, heap sort. We'll talk about heap sort again in this course, maybe from a different perspective. And we'll talk a little bit more about trees. And if time permits, we might talk about disjoint set data structures. But yeah, after that, we'll move into talking about graphs. You may have heard or seen what a graph is, or a network. We'll talk a lot about graphs. We'll lay out all the framework for that. We'll talk about some key properties and how we can represent these things called graphs. These are nice general structures. And we'll talk about some fundamental algorithms for traversing or exploring a graph. So a very common representation for, say, for example, if I give you a series of routes, I want to be able to go from point A to point B, and I want to find the shortest path from point A to point B. I can model this as a graph. So I'll be showing you a lot of different techniques and algorithms you can use to attack some of these graph theoretic problems. So it's a very powerful modeling tool, but also allows you to solve more problems. So we'll see some interesting applications here. And in addition, where I get really excited is this latter two parts here, where we start talking about algorithm design techniques. So some of these you will have actually seen in 210. I'm just going to formalize them a bit further. Other ones are going to be brand new. So I'm looking forward to exploring these here with you. And finally, the thing we'll end off with at the end of this course is talk a bit about complexity theory. In particular, we'll talk about this thing called NP completeness and this idea of intractability. What does it mean for a problem to be hard to solve? So we'll talk all about this in this course. And depending on how much time we have, I might get you to read a little bit on parallel algorithms. It's a little bit of a basic thing. Are there any questions up to this point? There's just a few other things I wanted to highlight before we get started. I'll just take a peek to make sure nothing's going on over there. I think we're doing okay. I think we're doing okay. But yeah, please stop me if you see or have any questions. Don't hesitate. I'm very happy to answer any questions. So generally, as you're here, we're here at the Zoom room. We're having ourselves a good time, hopefully. But yeah, so each week we'll be doing lectures, and I'll have office hours. They're just assignments that will be scheduled to be completed. These are just the links. Here's the link to the YouTube channel. It's already on your courses as well. Written notes, as I said, they'll be available after class. So after class, some point, give me maybe about an hour or two, maybe, sometimes a little longer, I'll post the lecture. So this is mostly just in case if you say you have difficulties copying down something from the board, or I ask you to, I point something to you and tell you to give it a read. It's mostly for accessibility purposes. And at the same time, I just want to make sure it's as easy as possible for you to learn. So I find very helpful for students to take notes during class because it's also another way you can rehearse this with yourself. And I find that's very helpful in a class like this. But this is a nice way you can go back if you ever find yourself needing to look over something or if you miss something. Yeah, as usual, office hours, they're going to be over Zoom. Most of this, I think, is pretty basic for most of you. There are 5 assignments in this course. Almost all of them are going to be purely written assignments. This is going to be a little different than, say, CS210, where you may have done a little bit more programming. You'll find in this course that there'll be less programming and more conceptual study. So there will be a little bit of programming in this course, where I think on assignment 3, I usually like to do a little bit of programming, and I think a bit on assignment 1. But generally, you're going to find that most of these assignments are going to be purely written assignments, where I'll give you something to try out on paper, whether it be trying out an algorithm, trying to design an algorithm. Heck, I might even give you an opportunity to try proving the correctness of an algorithm. And look at all these things as opportunities to learn about, to try to do the thing. That's really what it's all about. But just by general expectations, just try to be consistent with attending lectures and make sure you read any optional materials I point you to. I mostly point this out because obviously the term has started a little later than anticipated. So there may be a case where I may have to once in a while point you to something to take a quick read over it. But generally, emails, just try to keep them concise if possible. Try to use an appropriate headline if possible. It keeps things nice and simple and easy for me to recognize them. It's really straightforward. I know I don't have to explain a lot of these things for you. You guys are all pros at this. So just to take a look at the instructions I have here about assignments. So you'll include like a title page that has your family or last name, student ID, name, and so on. And you can, of course, type up your answers, or you can write them out on paper, take pictures, or scan them. I'm pretty flexible about it. But the one thing I will not be flexible about really is the deadlines, because there's going to be scheduled deadlines for each of these assignments. So I'll make certain assignments available, and then I'll make them have a clear deadline. I do not have a late assignment policy, so no late assignments will be accepted. However, I must point out one thing. And now this is the catch, because this is in fact an online course. Everything we're doing here, everything's being remotely delivered. So you might ask, Dan, well, what happens if my internet goes down or something? That's okay, because what's going to happen is when I give you a scheduled deadline, for example, if I tell you, okay, assignment 1 is due by the end of February 2nd, what's going to happen is I'm going to allow you to submit up until that deadline, but up until 8:30 in the morning that next morning. So on paper, the deadline will be the end of February 2nd, but I'll allow you to submit overnight up until 8:30 in the morning. The main reason why is because 1, I'm not going to look at it at 3 in the morning. And 2, and so it's one functional reason. And the other reason is because I know there's students in a variety of different places right now. I want to make sure I'm as accommodating as I can for everybody when it comes to these deadlines. So when there's no there is no late assignments, I mean in the sense that I won't accept anything until that next morning at 8:30. Anything after that, I won't accept. But hopefully this is understandable. It's pretty basic. I give plenty of time for the assignments. You'll have about, if you work it out on a calendar, I'm pretty sure it's pretty much 2 weeks per assignment. So that should be plenty of time for each one of the assignments. I usually try to design the assignments so that they should be easily completable within the time. So other than that, one other policy I want to point out to you is that whenever there's some issue with the grading, because the general rule of policy will be that if there's an issue with the grading, contact the TA that graded your assignment. The TA will tell you which, oh, I think we only have one TA in this course, so it's pretty straightforward. But if you have any disagreement with the TA about the grading, come to me and then I can talk to you about it there, and then we can figure out what's going on. So the pecking order is talk to the TA first, then talk to me, okay? But it has to be done within the 2 weeks of which the assignment grade was given. So just don't come to me like at the end of the term and be like, oh, my assignment 1 is just like, I didn't do as well on assignment 1. Can you take a look at this one problem? This is what this policy is about. It's just make sure that everybody's just dealing with these things as they come, as opposed to leaving it to the end. It keeps things nice and steady. The other reason why I don't usually generally have late assignments permitted in my courses is because what I do is I also tend to give the solutions to my assignments, and I try to do it as quick as I can. So make sure everybody has the ability to check over their work as soon as they can, as opposed to waiting for their assignment to be graded, which usually I try to make sure that the TAs stay on pretty consistently, okay? Just be aware that when it comes to the test, the midterm and the final, they're both being done with ProctorTrack. There is an onboarding quiz that's on your courses, so I'm asking you to complete that by, I think within like the first week of up till February, but it will remain open for the remainder of the term if you need to do anything with the onboarding. So I won't close it after that. It's just it's a nice deadline for everybody, because everybody sometimes needs a deadline just to get something done. It's a little helpful like that. But yeah, the midterm is closed book. It will be done during scheduled class time. It'll probably be about a 50-minute quiz. And probably that day I'll give you a shorter lecture. I'll just ask you to just watch a video, which will probably be like 10 or 15 minutes long, maybe. But yeah, no, just take a look at this carefully. There's some general policy in here. For example, there are no makeup midterms. And the final is on April 21st, 2022. And it's at the scheduled time. You'll be given about 3 hours, possibly 3 hours, 10 minutes to complete the exam. I usually like to make sure that there's enough time in case for accessibility reasons, you need to attach a file or something. But I must stress that these tests, both of them can be completed digitally by typing in boxes and stuff. There won't be a whole lot of file transferring or uploading to an assignment item. It'll be pretty straight. It'll be pretty down the middle, straightforward. But yeah, academic integrity, I'm sure you've heard this one several times, but I want to put my spin on it. Just keep in mind, remember, the assignments, they're meant to evaluate your understanding and give you an opportunity to apply the things that you're learning in class. So if you find yourself in a position where you're trying to look up answers, or you ask a friend and they give you a little too much, you're losing an opportunity to help yourself understand the material. In that sense, you're sort of cheating yourself from learning the material. So just keep that in mind when it comes to academic integrity. So keep in mind that all the work in this course is individual work. However, I must stress that if I do see anything suspicious, I will pursue it to the fullest extent. Just be aware of that. Just a few things. I'll bring up a couple of things around this policy in a moment, but I just also want to point out about tutoring. Now, I've been a tutor before. Like, I used to tutor for about maybe 5 or 6 years. Did a lot of tutoring in my time. A role of a tutor is just to help a student understand course material. They're not supposed to be doing your work for you. This applies whether it be an online tutor or an in-person tutor. So don't use a tutor to get your work done. The tutor is meant to help you learn the material. Other than that, just be aware, I do try to keep myself rather available over email, and I have plenty of hours for office hours if you do find yourself really needing some help through some of the things that we're learning here in the class. Also, of course, if you have disability or you need some accommodation, do reach out to the Student Accessibility Center for accommodations. I'm generally pretty flexible when it comes to this stuff within the context of the course outline. As I mentioned, recording policy. I am recording this lecture. This lecture will go up onto YouTube afterwards publicly. So if anybody wants to see what they're doing in class or something like that, or need to rewatch something because they missed maybe the first 10 minutes or something, these will be up, okay? Other than that, I will, like I said earlier, before I started recording, I will not be recording any student images or any private details of yours, whether it be your webcam or your name. I will not record these things. They're only the things that you see, what you see on your screen right now on the Zoom. That's only what's coming from me. That's the only thing that's going to be coming onto these videos, okay? So if somebody asks me verbally a question, it will not be in the video. Only part will be my response to it. So I'll usually reiterate the question if somebody asks me a question sometimes. But yeah, no, hopefully that seems okay. I generally don't have much of an issue with students recording the lecture. Just be aware that I know the university does have a recording policy, so just be aware of that fact. But if you have any questions about this, don't hesitate to reach out to me. I'm very happy to answer anything, okay? So just some general tips. So this brings me back to academic integrity. Just a couple of quick things. If you find yourself working on an assignment, it's encouraged to talk to your classmates. If you find yourself working on a problem and you're just like, oh, look, you're allowed to talk to other students about your assignments. That's something that I consider and I encourage if you find yourself it being helpful. However, remember that these assignments are individual efforts. So that means that you have to take into consideration that you can't just copy your friend's work because it saves you some time. What I generally recommend is if you're talking to somebody, do not give them anything written down for their own record. Instead, talk about it. Or if you're going to write it on a whiteboard, talk about it over the whiteboard. Don't take any picture of it. Don't pick up your smartphone and take a picture of it or something. Don't do it. It's very tempting to do. It makes it much easier to avoid just to not do that. Just talk about the problems if you need to talk about them. If you have any ideas, feel free to discuss them with your classmates. I encourage that stuff. But remember, your work is solely yours. So don't copy your friend's work. If your friend asks you, hey, look, can you help me write up this thing for assignment 2? Don't do it, okay? So if you're talking to somebody, talk about it, but write up your own solutions in your own time separately, okay? So if you're writing things on a board, erase the board after. Don't take any pictures of it. Don't write anything down. That's usually one tip I can give you to make things easier, to avoid plagiarism. Like I said, don't lose an opportunity to learn these things yourself. Talking to other students is helpful because when you discuss these things, it's also a part of the rehearsal process of learning. As usual, I recommend you start the assignment several days before it's due. Do it in little pieces. That's usually what I recommend doing. Tackle each problem in bits and pieces. I know some students don't necessarily take this advice, but I usually recommend doing it. You'll find that as I'm covering material, you'll find that you'll be able to work on maybe one problem or two problems after each one of the lectures. So you'll find that it'll sort of pick up and go at a pace that's generally where you'll be able to work on some bits of the assignment as we're going along, and I'll usually tell you what you can work on the assignment up to that point, okay? Just generally, like I said, try to meet with other students. It's usually a good opportunity to learn or discuss ideas from the class. And I always am big on encouraging other perspectives when it comes to generally, if you're learning something in this course, look at the optional text. If you find yourself wanting to pick up another text to learn about things, try to find another perspective to see if maybe it can affirm the views that you currently have. Challenge them. You'll find very often in this course, I'll pick up things and I'll talk about ideas in this class, and I'll try to convince you that what I'm writing makes sense. That's a very important aspect of it, is trying to be your own best devil's advocate. And that's something that is a very powerful skill to build up as a computer scientist, especially when we're talking about algorithm design. Anyways, that's all I really had to really highlight about the course outline. Are there any questions about the course outline? Just going to take a peek over there. I think I see something in the chat over there. What I'm going to do is if anybody has any questions with the course outline, I'm going to address them over there at the board there. That way I can see the screen over there. So let me just head on over there. So I'm going to boogie on over. So let's head on over back over this way, just to make sure I got everything. The onboarding. Oh, the quiz is expired. Okay, I'll fix that right after class. So thank you for pointing that out. Let me just see if there's anything else. Just want to make sure I got everything, because I know some people, it's a little hard to talk over the mic. So question about the assignment keys. So the assignment keys, what I'll do, so I do write up like full solutions for the written assignments. The only assignments I don't write up full solutions for are programming assignments, because usually the way I design the assignment, it usually tests your code, usually. But what I do is I post it, I try to get the assignment solutions up before you get your marks back, usually. That's why I usually like to make sure you have plenty of time in there. So that way you could look up things. Because I know sometimes you have it where you're waiting for a week or two for an assignment to get marked. I just want to make sure that you have the ability to check on something, especially when a test is coming up or something like that. Sometimes these things do come up. So I just want to make sure you have access to those things. So are handwritten assignments accepted for written assignments? Yep. Yeah, it's of course. Okay. Okay, so let me just see. Do I have names for my whiteboard friends? I always call this turtle the Java turtle because I used to have a dog named Java, kind of like the programming language. He had this droopy eye. She was a boxer cross, and she had these droopy eyes. It just always reminded me of that. This little birdie over here is pretty cute. I don't have a name for the birdie. If anyone has any cool names for the bird, I could definitely give the bird a name. But no. Are there any other questions about the course outline before we get started? Tweety's a pretty cute name. I like that. I like that. But yeah, if there's any other questions or anything, don't hesitate to reach out to me after class. Duolingo, I like that one too. No, wonderful, wonderful. Oh yeah, no. Yeah, no. One thing I will give you a heads up on, everybody. I know that there's some students here that have been in my classes before, or maybe seen some of my lectures. I do a lot of demonstrations in this class. So there's sometimes an incentive for coming to class, because then you get to see some of these demonstrations, and sometimes I ask fun questions. So you never know what might be coming in class. I'm not even kidding. I think the other lecture, I was chopping cheese up with a meat cleaver. I was doing some other stuff. I had a cat. I was doing mathematical induction with a cat. We have a good time here. So just, I know that some students, when they first see this class and they see the description of this course, they're like, oh man, it's got that dreaded M word, the math one, the mayonnaise. I can assure you that this class will have a lot of ideas that you're going to be exposed to. And I'm hoping that I'll be able to give some extra flair, some excitement, that you might be able to make it a little easier to understand the ideas. Because there will be a lot of things that we're going to see in this course. So, are there any last questions about the course outline before we get started? Give me 2 thumbs up if we're ready to go. Oh, wonderful, wonderful. Okay, why don't we get started, okay? So we're going to start off first with a little bit of an overview. So I'm just going to give us we're going to do this probably for the next couple lectures at least, where I'm just going to give us kind of an overview idea of algorithm analysis and talk about some terminology so that we're all kind of talking in a very similar way so we know what I mean when I say a certain thing. And I'm hoping to encourage you and kind of layer on top of some of the things that you've seen in 210, or you may not have seen in 210. Regardless, I'm going to make sure that you come out of this with some formal understanding of a lot of the things that you've seen in 210. So that when we walk through this in the next few lectures, what's going to happen is you're going to be like, okay, that's what Dan means by a problem. That's what Dan means when he talks about an algorithm. That's what Dan means when we talk about this, this, and this. And these are very common ways that people tend to talk about a lot of these things. So you're going to find this framework that I'm going to introduce to you this day, and probably the next lecture, pretty helpful for this. So for some of you, this might go pretty slowly. Some of you might find this very intriguing. So it's going to be a little all over the place. But please, if you have any questions, don't hesitate to let me know, okay? I'm very happy to answer any questions. So let's start off with probably one of the more basic things that I think is important before I get too far ahead of myself. In computer science, one of the core things that computer scientists are interested in is problem solving. So I need to come up with some definition. Now, this isn't going to be a perfect definition. It's not overly formal, but the way the framework is going to work is it can be quite formal. We need to talk about what a problem is, to talk about problem solving, at least in this course, because I'm going to have to pin things down. Now, in courses like 411 or 412, you may talk about problems in there's a much more rigorous way of even casting this definition. But you're going to find that this definition is going to be really helpful for us. So I'm just going to keep it rather basic for us. So a problem is just going to be simply a question or statement that requires solving. That's the first part of it. You're going to find that this is not really the interesting part for us. This is just a broad net. This is the part that's going to be interesting for us. So a computational problem, is, just to keep it broad as I can, I'm going to include it to be n infinite. I'm just going to put parentheses here just because sometimes people can define problems with a finite number of what I'm going to say in a moment. But the ones that computer scientists tend to be interested in tend to be an infinite collection of possible problem instances. So don't worry, I'm going to give you an example of what I mean by this, of possible problem instances. Just going to switch my marker. This one's being a little funny. Problem instances. So I'm going to define what a problem instance is. This marker is doing a little funny for us. I'm just going to chuck it that way. It's gone. It's gone. So anyways, each problem instance, I have bad luck with my markers today. Each problem instance which I'll abbreviate as instance. So if ever I'm saying instance, I'm meaning problem instance. Okay, I'm going to switch this marker too. This marker, like I said, I have some weird luck today. It's gone. It's gone. It's gone. Let's keep going. I'm hoping number 3 won't be as bad. Let's do this. Abbreviated instance. Okay, that one's much better. Very good. Phew. I didn't want to keep chucking markers. So I'm going to call a problem instance an instance as an abbreviation. I have to be very careful when I'm doing this. Of a problem has inputs, which usually if I need to be more explicit about what I'm talking about with the instance, I'll sometimes call this an input instance. But usually when somebody talks about the instance, they're talking about the inputs. And upon being solved, has a solution. So you'll notice that my definition of a problem is rather constrictive. If you care about problems that don't have solutions. They aren't problems in this definition. So just keep in mind that this is just a broad definition we're going to use. I'll adapt it and formalize it in different ways depending on what's useful for us to talk about. So first, before I proceed ahead, are there any questions about my definition here? Does this seem okay? So I'm going to draw you a picture here in a moment. Actually, let me draw it here. I have space up here to draw it for you. So when we think about a problem, in this sense, so imagine so this whole circle here, this oblique shape, it looks kind of funny. If I call this problem capital Pi, each one of my problem instances are going to be inside of my circle here. And each one of these is going to be a problem instance. So if I give it a name, I call it like X. I'll say X is an instance of the problem. So this just means in. So if you think of this problem as a collection of instances, you could think of pi over there as what we would call in some mathematical ways, we would call it a set. So it's just a set of instances. So I have a question for you. Could somebody let me know or type it in the chat? If I consider problem pi, and I want to tell you, hey, look, I came along with my really cool algorithm. And I have this algorithm, and I propose to you that it solves the problem. Is it allowed to omit any of these dots, or does it have to consider all of the dots? So if I told you my algorithm solves problem pi, does it have, can I like cherry pick the dots? Yes, exactly. You should consider all of them. So this is why problem formulation is going to matter a lot in this course. So you're going to find that when I talk about a problem, every single time it's going to be well formulated like this. So every time I'm going to be able to tell you what an instance looks like, what the inputs are, and what the solution should look like. So is that clear, everybody? So I'm going to give you examples of what these would look like in a moment, okay? So just I like this picture because it's rather helpful for seeing, okay, because very often when you study algorithms, sometimes people they think, oh yeah, no, I don't really care about that one. It works pretty good. It gets these dots really well, but those ones, not so much. It doesn't give me a solution all the time. We wouldn't necessarily say that that would solve this problem in this sense. Hopefully that's clear, everybody. So we'll talk more about that in a little bit. So if we're okay with this, I'm going to proceed now to introduce another idea that you may have seen in 210, you may not have seen it in 210. Regardless, it's going to be an important concept that's going to creep into things every once in a blue moon. Now, I'm pretty sure you've probably seen it in 210, but you'll find that in this course, it's going to come up a little more often, but in some of the weirder or stranger ways that you may not have seen in other courses before. Most of the time, it's just going to be just like how you've seen it probably in 210. But there's going to be sometimes, and I'm going to put it imagine I was wearing a cool hat and I have a feather. I'm going to put it in my hat. Imagine you had a hat like that. It's going to be very much like that, where I'm going to tell you, I'm going to come back from the future and I'm going to say, in this first lecture, I told you this one thing. Now it's going to be relevant. There's going to be some point near the end of this course where that's going to happen. So just be aware that will happen. But for most people, this is going to sound pretty sensible what I'm going to introduce. I'm going to talk about input size. You may have heard of input size before. You may have heard of it called input length. In the context of algorithms, this is how we usually are going to talk about it. So now each one of our problem instances, I would like to be able to define it to have some size. So So each problem instance X for a problem pi has its own size. Now I'm going to give you the formal definition first, and then you're going to find that most of what I'm going to do with the input size is going to be just like how you did it in 210. Just there's going to be some times where we have to be a bit more careful, but it's not going to happen very often in this course. So, formally, input size, which I'll sometimes, if I need to be very formal about it, I can use these bars to indicate the length of this input. Now, if you're wondering what X actually is, so remember, if you think about it in terms of a computer, when I want to solve a problem on a computer, say we were considering sorting, for example, and I want to have an input array A, and I want to sort A. Each one of the instances, as I'm going to tell you in a little bit, is an array of length n, right? Where n is just the length of the array. Now, on a computer, we would encode that information, what the array is, as what? What would A actually be? Like on a computer. Think of the most fundamental thing you can think of. Well, it would be at a memory address, but what is it encoded as? Starts with a B, Yeah, it's in binary, it's bits. So you can think of this input size as the number of bits needed to encode the instance. In fact, that's pretty much what it is. Formally, input size X, which I'll usually give this a more friendly name as opposed to these bar notation. If you take a course like 411, we use this notation a lot. So input size X is determined by, I'm getting a little ahead of myself, is determined by the number of bits. And I must stress that it doesn't necessarily have to be bits. This is where it gets a little strange. As long as it's any reasonable encoding scheme. And you might ask, Dan, what does that mean? Or any other reasonable encoding scheme. What I mean by this essentially is that if you can encode your information in base 3 or base 64 or base 12, base say 16, it doesn't matter. It doesn't matter. That's what I'm saying. The only outlier of what wouldn't be a reasonable encoding scheme is whatever does not make sense for your computer, and the one that is universally the one that does not make any theoretic sense to use is unary, believe it or not. Why? Because when I write out my information as just ticks, as strictly just ticks, when I measure this in terms of the running time, imagine I want to write out like a number, like 20 or something. I could write that out as 20 ticks. Now, imagine I have to go through all 20 ticks. Now, I would have to go through all 20 ticks, right? If it's in unary. In binary, there's a nice exponentially smaller representation of that with a logarithmic number of bits. Unary has a very interesting relationship with some types of optimization problems that we're going to see towards the end of this course. But yeah, that's the outlier. Basically, most things are going to be reasonable encoding schemes except for unary. Unary is the weird one. But if you have any questions about that, don't hesitate to stop me. But we will not really go into much detail about that. We'll just assume that it's just encoded with bits. That's really it. Why? Because that's just the one that most people are encountered and equated for. It's a good time. But yeah, this is a usual definition. It's just how many bits you use to encode the instance. The number of bits are required to encode. Formally, input size is determined by the number of bits, let's say, required to encode it. There we go. Very good. Sorry, I'm just getting very excited about telling you about input size. So, are there any questions about this definition? I'm going to give you some examples. And you might ask, Dan, why should we care about this? So often, the larger the input size is, the longer the algorithm takes. The algorithm takes to run in the worst case. You might ask, Dan, why would that be the case? Well, think of it. Usually when you deal with a problem, usually you have to look at the input, right? If the input gets longer or larger, then you're going to have to probably process more data, right? It's a very common thing that happens in algorithms. And we'll see lots and lots of examples of this in this course. So just some examples. So you might ask, Dan, are we actually going to like sit down and actually measure all of these bits out and calculate it out and that? No, we actually don't have to do that. There's actually some interesting reasons why, but depending on how much time I'll talk about it. But I'm going to tell you about reasonable ways we can encode the input size. Examples of reasonable considerations for the input size. So you're going to find very often that you don't actually have to sit down there and write out like how many bits it's going to be. It's going to be log base 2 n of bits and stuff. That's not going to really need to come up very often. There's only really going to be one time in this course where it's really going to come up. So just to be clear about this. For the vast majority of the time, reasonable ways of encoding the input size are things such as this. So the first one I mentioned, so imagine you're sorting an array. So imagine you're sorting an array of length n. Can somebody tell me what did I say was the input size there? So if I have an array, if I'm given an array of length n, and I want to sort the elements there, what would be the input size? N, exactly. So this would be a reasonable consideration of the input size. I'm going to tell you why we don't have to actually sit down and actually measure these. You can if you want to, but it's absolutely unnecessary for most of the problems we look at. Yeah, so the input size is n. So this is a reasonable way of considering it. You're going to find in most cases, just considering the number of elements that are in your input is what's going to be the input size. Why? Because most of the time, the algorithm's running time will depend on the number of elements, not what the values of the inputs actually are. I'll talk about that in a moment. So imagine if also, say for example, I give you a binary tree. So to traverse a binary tree T, Sorry, my writing's sort of melting in the microwave here. That says binary, by the way. Traverse a binary tree T. It can be the number of nodes in the tree. The number of nodes in T. So you'll notice that most cases it will be like this. Another example. This is one that's a little bit more of the outlier in this whole situation. Determining if a number is prime so if I want to determine if a number is prime and the only input I'm given is an integer, do we have to be a bit more careful about how we measure the input size? Because remember, I'm only given a number, and most certainly the algorithm's probably going to have to examine that number. So in this case, do I have a whole bunch of elements I have to look at, or do I just have one? I just have one. But the problem is that when I'm going to examine an algorithm that checks if a number is prime or not, it's most certainly going to examine it. Well, keep in mind that the T over there involves the tree. My apologies. So here's where you might actually want to consider when it's the number of bits. Yeah, because you'll have to probably compare the number against other numbers, probably. For example, if we're doing something more with a cryptography-based application, you may, for example, have to adapt a so-called sieving method, for example, or a possible testing method. So in this case, you may actually want to, in this case, determine if a number is prime. I'm sort of running out of space here. Let me just jam it in right here. My apologies. If the number is prime, then the input size is the number of bits. It's the number of bits. The number of bits to represent that number. So you see how, for different problems, we might actually consider the input size a little bit more delicately. So for a number theoretic problem, like determining if a number is prime or not, we might actually go a little bit more careful and actually go to this formal definition. For most cases, like we're going to see in this course, we're just going to simply need to look at the number of elements that are in our collection or container that we're looking at, okay? So are there any questions about this? So I'm going to tell you the real, I'm going to give you the lowdown of what exactly I'm going to have to take as our classification of okay, so what do we do with numbers then? So I'm just going to give you one important detail that will help you really navigate this concept of input size a lot easier. Because you're thinking oh, well, there's these bits I have to encode, and then there's all this, there's stuff about number of elements. You might ask, okay, well, what do we do? Sorry, the camera was looking at something. it was kind of going that way. There we go. So we will assume the numbers are, now keep in mind when I say numbers, I mean in the most broadest sense. So when I talk about an input, I mean when you encode that as in binary, that's also a number, right? That's what I mean. So we'll assume the numbers are encoded using some fixed number of bits. Now you might ask, Dan, what does that mean? Well, here's the simplest way you can think of it. And this is exactly what you run into in practice. So for example, when you use, say for example, in a programming language like C++, you use a variable like int. That's representing an integer that is using some constant number of bits, right? Just like if I use a floating point number, the floating point number is using some fixed number of bits, some constant number of bits, right? This is something that we run into all the time. So here's the underlying assumption that I'm making when I write something like this. This is just going to sound really weird at first, but I assure you it actually makes a lot of sense if you actually think about it just in the setting I just described. I'm going to assume the computer is capable, so any computer I'm going to look at, hypothetically speaking, when I analyze these algorithms, are going to be sufficiently powerful to be able to actually read all of the words in this fixed number of bits. So if it's, say, 32 bits, that's okay. It's just some constant number of bits. If it's 64 bits, it's some constant number of bits. If it's 128 bits, it's just some constant number of bits. The point is that when you go from, say, one encoding scheme to another, and if it's using some fixed number of bits, it doesn't matter. It's just some constant factor, right? So, and this matches your intuition, right? So when we work and develop programs on a computer, almost always we're working with data types that are encoded with some fixed number of bits, right? So when I have an array of length n of a whole bunch of ints, you would agree with me that it's just going to be some constant factor times n, right? So it's going to be the number of bits needed to represent the int times the number of integers, right? So that's what all I'm saying here. So what does this mean for us? So I'm just going to append onto this sentence. I'm just going to go i.e. input size depends on the number of elements. The number of elements or items in the input. So, the big caveat with this is that whenever we run into a running time with an algorithm, and that number, a number pops up in the running time, that is like one of the actual numbers in the input, we have to be more careful because remember, the input size over there is measured by the number of bits. If one of these numbers pops up in the running time, that might be trouble for us. But that almost never happens in this course. Are there any questions about that? So the big takeaway here is we always, for the problem you consider, for any problem you consider, you need to specify the input size and do so carefully. Okay, so are we okay with this? Just want to, if there's any questions on input size, don't hesitate to stop me. So for most cases you're going to run into, it's just going to be the number of items or elements in your input. Why? Because our algorithms typically don't want to design them so that the numbers themselves pop up in the input. That happens sometimes in problems involving numbers. As I said, towards the end of this course, we'll see an example of where this might happen. But the cool and interesting underlying theoretic reason why I'm saying this is that this almost effectively future-proofs our work, if you think about it like that. Because I'm not telling you that, oh yeah, no, there's some arbitrary bits that I'm saying. I'm saying that, oh yeah, it doesn't really matter. It's just some constant number of bits. It doesn't matter if it's 20 years from now, if they change the architecture or something. The ideas I tell you with input size, they don't change. So are we okay with that? But yeah, there's both a practical reason in the sense that, oh yeah, all our data types that we use all the time in our programs are always usually of a fixed size. That's where we have to be a bit careful, right? If we have an arbitrarily length data type, that's a bit of a problem. But usually if we're talking about primitive types, not a big problem. Okay, so if we're okay with that, I'm going to talk about problems some more. So seeing as I talked about problem and an input size, let's talk about some examples of problems. And I'm sure you've seen these before. So for example, we talked briefly about sorting. So here's an example of a problem. So given an array A with n elements, return A in non-decreasing order. So that's one example of a problem, right? So you can see that from the way I've written this, you can identify what an instance of this problem looks like, and you can see what exactly a solution looks like. Does everybody see that? So when somebody gives you a problem formulation, your goal is to try to cast it in a way so that it's very clear what the input and the outputs are. So you'll notice that our frameworks are just built around input-output. So here's another example of a problem. This is one, both of these are ones that you've seen before. But most certainly we'll touch upon them again and again and again. They're sort of fundamental like that. Here's another one, search problem. So given a set S of n elements and an element X, return whether X is in S or not. So I have a question for you. Question. If I'm talking about these two different problems here, can somebody tell me an algorithm that solves the sorting problem here? I know you've seen at least one. In fact, I'm sure you've seen several. Yeah, merge sort. Merge sort's a good example. So that's an algorithm that solves the sorting problem. Okay, how about the search problem? So suppose if the set S was an array. So suppose S is an array of n elements. Can somebody tell me an algorithm you can use to solve this problem? And I must stress, we're going to come back to this one of these algorithms. Well, that's a good, I'm going to talk about binary search in one moment. That's a very good guess. That's not the one I'm looking for. It's a very good one, but that's not the one that will actually solve this problem specifically. I'll come back to that point in a moment. Linear search works. Linear search actually solves this problem. Do you notice that the reason why binary search doesn't actually solve this problem is because I'm assuming any arbitrary array as the input. So if I use linear search, for example, I can use that to solve this problem in linear time. However, if I knew that the inputs always were S being an array that's sorted, then most certainly binary search would be able to solve that problem. Some people would call that a special case of the search problem. That's a wonderful, it's always an opportunity to bring these things up. But is the concept clear to everybody? But yeah, if we're all good, excellent. I'm seeing some thumbs up. Excellent. Give me 2 thumbs up, by the way. Awesome. Awesome. Okay, good. Keep in mind, if you have any questions about these things, don't hesitate to stop me. I'm going mad with power here. I'm just joking. Anyways. So just 2 things I want you just to be aware of. Just as a reminder, is remember that there's really kind of 2 main things in this course that you're going to run into. Data structures, which tell us how we can organize data. And normally these are casted as ADTs, or abstract data types, which have a set of operations. You're going to find in this course, when we encounter new ADTs, I'll tell you what their operations are, and we'll often look at different ways we can implement that data structure as, well, the ADT. So you've seen plenty of examples of these. For example, you may have seen a stack, you've seen queues, you've probably seen, for example, you may have even seen of something called a dictionary, for example. Some people call it a map. You may have seen lists. These are a lot of different kinds of ADTs. Now, excellent bringing up a heap. I'm going to talk about heaps in this course. If you've seen heaps, that's awesome. But I will talk about those as well in this course. We'll talk a lot about heaps. But that's one element that you're going to keep in mind with this class. The other one is, of course, our concept of an algorithm. So I want to talk about what an algorithm is for our working definitions, okay? So I must stress that there is an even more formal definition of an algorithm, but that is going deeper than this course. So some of you know this definition if you've taken a course like CS 411. For most intents and purposes, and for functional reasons, you'll find that this definition of an algorithm will suffice for us. So let's talk about what an algorithm is. So I'm just going to give us kind of a big picture look. So I'm going to write out what an algorithm is. At least our working definition. If you talk to somebody that works in algorithms, they'll say, yeah, that's pretty decent. That'll work for us. There's a more formal way of talking about these things, but for us, this will be good enough, okay? Because functionally, it works exactly what we would need it to do. So our definition of an algorithm is going to be an unambiguous, so that just simply means, so it's an unambiguous, actually I'll tell you what this means in a moment in case you're not sure what unambiguous means. An unambiguous step-by-step procedure that takes an input instance of a given problem as inputs and produces output for the problem instance. So you notice that our intuitive definition of an algorithm. So most people, if I were to take a course, if you take a course like 411, I'll tell you that this is pretty much the intuitive definition of an algorithm. But the point is that notice that my definition here is actually working fundamentally with our notion of a problem. It's baked right into the definition. So when I mean unambiguous, the biggest part of this is you should be able to communicate it to somebody such that they won't be able to misinterpret what you're saying. So for example, if I am talking to somebody about an algorithm, if I can communicate it in the language for which they speak, or if it's a computer, which is rather why algorithms are rather useful for computers, is because there is an unambiguous way of communicating operations on a computer, right? Unambiguous simply means there's no way you can misinterpret what exactly is being written or communicated to you. So you have to be very careful when you're communicating what an algorithm is, whether it be in English, which you'll find very often I will do, or in what we'll call pseudocode, which you may have seen in 210. So here's just a big picture, just to give you a general idea. So it just simply means There's no way you can misinterpret what they say. So here's kind of a picture to kind of put everything I just said all together. So here's a problem. There's all my instances. So if I blow up one of these dots, so I'm going to blow up one of the dots. I'm just going to make it really big, just because it makes it a little easier to see. So one of these dots is an instance. So it's an instance x, so let's call this x, of pi, and it has inputs, which it's going to be x, that's what x is, and it's going to have a solution, so there's inputs and there's a solution. Keep in mind, when we talk about different types of problems, we might formalize this a little differently. For example, later on in this course, I'll talk about optimization problems. There's a more formal way of talking about this in a little bit. So if I give you an algorithm with my definition that I gave you here, this isn't really mine. It's just a colloquial one that's used informally by algorithms people. It has two parts, right? It has inputs. It has inputs. And it has output, right? So it takes input and it produces output, right? So all I've been describing to you up to this point is that the input is given to the algorithm. So it gives x. So it gives x to the algorithm as input. And what we would like to know is the output correct or not? If we could do this for all of the instances, then we could say our algorithm is correct if it's correct output for all of them. So just in very exact terms, if I want to solve a problem, my algorithm has to be able to pick up any one of these dots I have over here. It takes the input from the instance, it could process it, produces output, and if it is correct output, then we say it produces. It is in fact going to be the case that the algorithm is correct because it solves the problem for every one of those instances. So is that clear, everybody? If not, feel free to stop by. I'm going to be around here for a little longer, but we're going to stop right here. I want to say thank you very much, and I'll see you on Thursday, okay? Have yourself a beautiful day. I'll see you later.